Hi, my name is Jonas, and today I want to show you the table saw that I built over the course of the last 4 months. The table saw in itself is not that big a deal because there are more than 100 YouTube videos that show people building their table saws. So I won't focus on that aspect. What I will focus on is the computerized electronic fence control system that I designed, built and implemented in software by myself, so there is no point in asking me, where did you buy it? I didn't. However, in the comment section below, I provide links to important components used in my system. Besides controlling the fence, the computer also controls the blade height. Now let's move on to operating the system. First, I am taking out the user control module right here, or the user interface, and I'm also turning on my camera that takes a good look of this interface, because the details on the interface are not visible on the main camera that I'm being filmed with. So here it goes. The main points about this user interface that I have to go through before I can show you an actual demo are the 2 displays, of which we are really using only the lower display. So this is the only display of interest to us. On this display there are 2 columns, the left and the right column. In the left column we see the actual position of the fence relative to the blade, and in the right column we see the set point. That is the position of the fence that we would like to have. Furthermore, there are 3 rows of numbers right underneath the headings of actual and set point. The rows of numbers mean the following. In the first row of numbers, we see the actual position or the set point in units of centimeters. In the second row, we see the actual position or the set point in units of inches and with a decimal notation. In the last row, we see the actual or set point in units of inches, but in fractional notation. So if I want to go ahead and set the set point to 30 inches, I use one of 2 encoder knobs which are labeled whole or fraction. The whole sets whole numbers of units, and the fractional encoder knob sets fractional parts of the set point. Also, I need to explain that there is a 3-position switch that allows me to choose in which type of units I want to enter the set point. In this case, I want to go to inches in fractions, so I'll go right ahead. I'll set some easy number. Look at this row, this is what's of interest here. I'm going to 30 inches, like so. And next I hit the run button to make the fence actually go there. So now I believe that the fence is at a distance of 30 inches from the blade. And to verify that, I have to do one other step, and that is I'll use this here 3-position switch. For now I'm only mentioning the 3rd position, which lights up the blade LED, and that means I'm now going to control the blade. To control the blade, I'll just go and tell the blade to extend by 1 inch. And so there is that. Now I can measure the distance between the blade and the fence. I lock the distance in, and I'm reading it here. It is 30 inches exactly, no fraction, no nothing. 30 inches exactly as I had set it. To further verify that this stuff works well, I will now set a fractional component for the desired distance between the fence and the blade. And so I'll go ahead and say, this looks good. 3/16. Now I will tell the fence to move to a position that is 30 inches and 3/16 of an inch away from the blade. There was that, and we'll take another measurement. I'm locking the result in, and I'm hoping that you can see that it is 30 and 3/16, exactly as dialed in. Next, I'll show you another function, and that is summoning the fence or the blade back to the home position. That button accomplishes that. The home position has a calibration step that has to be performed only once and then never again unless you make substantive changes to your saw table, in which case you have to recalibrate. The calibration is not difficult, but I don't want to distract from the features that I really want to show you. For now, I have shown you the way the fence can be set to a position that is called an absolute position. It is absolute instead of the other way I can control the fence called relative. In the relative mode, I will be able to move the fence just a little bit. For example, that would be if I want to cut a dado with the saw blade. I'll give an example of that. I'll actually show you, and for that I'll reset the set point from the last set point that it was at. I'm resetting it to 0, and now I'll set a new set point. I'll actually work in centimeters for that because I can measure that more accurately. I'm setting the input system to centimeters, and I will tell the fence to move to a position of, here now the centimeters are of interest. I'll tell the fence to move to a position 3 centimeters away from the blade. Okay, there was that. And I had prepared a few boards of wood. And in order to show you how a dado can be cut, I'll reduce the blade height to something more modest, like let's say 3 millimeters. For that we watch this display here. The display is in centimeters, so 3 millimeters are 0.3 centimeters, just like I set it now. And here the blade is moving. Now we are ready to cut our dado. I'll put my safety goggles on. Okay, here we go. So now, first of all, let me verify that the cut was actually 3 centimeters from the blade. I'm using a caliper because it provides greater accuracy. I'm getting a reading of 29.8 millimeters. That is off by 0.2 millimeters from the position that I wanted to be at. Let's say I want a dado of 8 millimeters width. The first cut has the width of the saw blade which is about 2 millimeters. And if I want a dado exactly 8 millimeters, then I have to do 3 more cuts 2 millimeters apart from each other. And to do that, I'm going to use the relative feature in the system. I put the switch on the relative position, and I'm resetting the set point because now we'll be working in very small increments of minus 0.2 centimeters, or that is the same as minus 2 millimeters. The minus sign indicates that the fence will move closer to the blade. If it was without the minus sign, the fence would be moving away from the blade. So now I'm telling the fence to perform this move. There was it. It moved by 2 millimeters toward the blade. Now I can do the next cut. And in quick succession, I'll just hit run again and do the next cut. So now let's see what we've got. We made an original cut that was 2 millimeters wide. Then we added 3 more cuts 2 millimeters apart from each other. That should amount to a total of 8 millimeters. I'll use the caliper for this measurement. And the measurement that I'm getting is exactly 8 millimeters. 8.00 millimeters is the width of this dado. I'll check another position. Here it is also 8, and another position, here it is 8.02. In either case, I made a dado 8 millimeters wide, and for doing that I used the relative setting, which allowed me to quickly, with just a push of a button, to move the fence by the desired amount. I will go into some further details now, and if you're not interested, this would be a great time to tune out. Otherwise, if you want to know more about the system, I'll just tell you more. So the system is based on this control box. The control box is not much. It's really what you see, that's what's in the control box. The control box is merely a box with all the buttons and switches and lights and LCD display, but no other electronics is in here. The other electronics is sitting in this box here, which I don't really care to open as it is currently closed, but I tell you that inside of it is a microcontroller called a Teensy, specifically the Teensy 4.1. If you don't know what a Teensy is, you're in good company. I also didn't know until a few years ago. Before that, I only knew of a very popular microcontroller called Arduino. And the Teensy, as it turns out, is just the same as an Arduino, but on overdrive. It's about 100 times faster, has 100 times more memory. Luckily, it doesn't cost 100 times more. So that's a great choice for anything that requires very fast computation, as is the case when you want to drive the motors that are used in the system. So let me switch to the motors now. This here is one such motor. It is a special motor called a stepper motor. If you are unfamiliar, a stepper motor is in a way like a DC motor, and it is driven by a DC voltage. However, a stepper motor otherwise works very differently from a DC motor. A stepper motor responds to pulses. Pulses generated, for example, by a microprocessor like the Teensy. For every pulse that the stepper motor receives, it advances, it rotates a tiny little bit. How much? Well, in this particular case, 1/800th of a full rotation. So that's less than 1 degree. It's about 1/3 of a degree or so. If I want the stepper motor to rotate and rotate fast, I have to send it a truckload of pulses every second, 1,000 pulses maybe per second, or more than 1,000 pulses. And to do that accurately, you need a faster microprocessor such as the Teensy. Now, the stepper motor, once it gets those pulses, it rotates, and it then, I can't rotate it right now by hand because the system is turned on. It locks the stepper motor, but I can rotate it by using another function that's available to me here in the control box, and that is the jog function. As long as the jog button is pressed, the motor rotates at a slower speed than its maximum. So you see the motor is rotating, and the motor is connected to a lead screw. And this particular lead screw is very popular and has become quite inexpensive because it is widely used in 3D printers. This lead screw is designed in such a way that for every full revolution that it makes, it advances this carriage by 2 millimeters. So there is an exact correspondence between how many rotations the lead screw does and how far the fence advances. Of course, there is a second such system on the other side of the table that we can't see from this position. It looks exactly like this one, 2 systems. And the reason why I chose stepper motors for this application is that it is very easy to make stepper motors run at the exact same speed and through the exact same distance, simply by sending both of them the same number of pulses. So if I send this motor 1,000 pulses and the motor in the back 1,000 pulses, then they both advance the exact same amount. And if I otherwise coordinate the pulses so that they happen at the same time, then they move in unison, synchronously along, and keep the fence nice and parallel to the saw blade. Last thing that I should explain here is the mount itself. This portion, this is readily bought. I can't do the metal work, I can't cut the lead screw, I can't build a motor. All of this is readily bought, and it is together as an assembly. It is called a linear actuator. Linear because it moves straight and not in rotation. I should explain the following. Stepper motors are as great as they are for controlling things in synchronization with each other. They have one problem, and that is the following. If for some reason the path of the stepper motor was blocked, for example, and that's a real example that happened to me a few weeks ago, I had a clamp mounted in the back. I had a clamp mounted there because I was doing something else. Then I forgot about the clamp. I tried moving the fence, and sure enough, the rear end of the fence hit the clamp and couldn't move anymore. So what does the stepper motor do when it can't move? It slips. That means it receives pulses but doesn't do anything. And who would? If there's a clamp in the way, the motor can't move, and so it didn't move. Now, if this fence was rigidly connected to both linear actuators, and if one motor stops while the other keeps moving, things would break. That's not good, and so in order to avoid such breakage, I designed the fence in the following manner. I'll bring it a little closer to the camera. So first of all, I can remove it, which is a necessity because sometimes I just want to have the whole table for some purpose other than cutting lumber with it. Now, what I did here, I made these holders for the fence, I made them movable and removable. Right now I removed it, and if I wanted to put it back in, I have to take a look. It goes in here. I hope you can see that. It goes in here, and this allows for the possibility that one motor stops. Let's say if this motor was stopped due to an obstacle and the other motor was still moving in this direction, then this vertical post would simply detach from the fence without anything breaking, and that would save the day. Now that I've explained how the linear actuators move the fence, I want to show you how a similar linear actuator extends or retracts the saw blade. In this scene, one camera is looking at the DEWALT circular saw mounted underneath the table, while a second camera looks at the saw blade above the table. The saw's depth adjustment is unlocked, which makes it possible to have a linear actuator raise or lower the saw. A vacuum hose is attached to the optional dust port of the circular saw. A shop vac, not seen in this view, is located directly behind the vertical back wall of the saw compartment. There's one more feature that I would like to show you, and that is on my phone. So please bear with me as I bring up the app, and then we'll turn our attention to the table. The app has a name. It's called RoboRemo, and I just brought it up. I'm also recording it on the phone, so it's not really necessary to see it well on the camera screen. And this is how it works. I tell the system to connect to my table, and I see that I'm connected now. And now I have a user interface here that I built from the RoboRemo toolkit, and with that interface built, I can do everything I can do with my hardware user interface. For example, I can raise the blade by, let's say, 5 centimeters. There. Or I can tell the fence to move by, say, 20 inches. I'll go 25 inches. While that's happening, I can tell the blade to retract. And one more example of what I can do here. I'll jog, and there I'm jogging the fence. And it stops, and now I tell the fence to go home. And that's that. RoboRemo, pretty cool stuff. And with that, I want to complete this video. Thank you for watching. If you watched until now, you really have a lot of endurance. Thank you very much. Bye-bye.